Alright, so here are our 3-4 perpendicular lines notes, and we're going to have the objective of proving and applying theorems about perpendicular lines. There you go. So, we're going to talk about a perpendicular bisector and also distance. In 3-4 here, our official definition of a perpendicular bisector is a line that's perpendicular to a segment at the segment's midpoint. Super. So we have talked about bisector already, but this is going to be specifically a perpendicular intersection. So you can see here that we have the 90-degree block in there because perpendicular means meets at 90 degrees. And so that's why that little box is there, to indicate that that's happening. You'll also see these tick marks here, which indicates that you have two parts of that segment that would then be the same length. So lots of things happening if you insert a perpendicular bisector. 1, things are meeting at 90 degrees, and 2, things have been bisected, or cut in half, or equal. Alright, then we have distance from a point to a line, and it turns out that the distance from a point to a line could technically, take on a lot of roles. For instance, this is the point, this is the line, and we could have met that way as well. But whenever they say distance, they actually mean at 90 degrees. So if we take a line, and there's only one, from that dot that we're looking at to the line itself, it must meet at 90 degrees. Otherwise, it's not the distance. It's just a length. So officially, it's the shortest segment from a point to a line, and it's the distance between the point and that line. So whatever that length happens to be. And the segment, of course, is perpendicular to the line at that point. So using this knowledge here, we'll take a look at a few theorems. So we have our perpendicular lines theorem, this first one here. If two intersecting lines form a linear pair of congruent angles, so notice that we have two angles on a line together. That's a linear pair of congruent angles. They also have one tick mark on both of them, which would mean that they are congruent. Then the two lines are perpendicular. So the only way if a linear pair is going to work is if this side is 90 and this side is 90, because otherwise it will not make the 180 needed. So if you have two of the same angles that are a linear pair, guess what? They better be 90 and therefore 180. So perpendicular. You'll also notice here that we have our perpendicular symbol. I can't remember if we've done that yet, but it's an upside down T. Basically, it's a set of perpendicular segments. So that's the whole idea. All right. Then we have the perpendicular transversal theorem. So the perpendicular transversal theorem says that in a plane, if a transversal, so that guy there, is perpendicular to one of the lines, guess what? It's perpendicular to the other. And of course, that is by corresponding angles. Because if this one up here is 90, this one down here better be 90. Otherwise, those are not parallel lines and doesn't work. All right. And then the last one here about perpendicular lines says that if two coplanar lines are perpendicular to one line, so if we have two lines that happen to be perpendicular to another line, then those two lines are going to end up being parallel. So we're going to get parallel lines from those right angles. All right. They also have these very long titles for this theorem. Two intersecting lines form a linear pair, blah, 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 blah. Again, that's just the name of that one, which is why we don't necessarily call it that. We just say it's a linear pair that's the same, so that must be 90 degrees. Anyway, no good name for those. That's simple. Alright, so we're going to prove some properties of lines here, and so we're going to write a two-column proof for the fact that R and S are parallel, and 1 and 2 are the same. So, R and S are parallel, and 1 and 2 are equal is our given. And we need to prove that R is perpendicular to T, and so notice it's written down here. And so we just need to look at our diagram in order to get there. So, they're also telling us there must be a reason that 2 and 3 are the same, and that's because R and S are parallel, and so this is the transversal, which means 3 and 2 are corresponding angles. Alright, then we're going to do some substitution. Because guess what? Instead of a 1, instead of a 2, we're writing a 1, and that's because of this identity up here. And so that means that all we have to do is identify that r is perpendicular to t. And so r is perpendicular to t by our previous theorem, because we just talked about by course, whoops, sorry. I was trying to erase that. We're going to actually do it by this one here, 3, 4, 1. So we're going to say if it's a linear pair, then there's perpendicular. Officially it's going to be 3-4-1, but we're going to say if linear pair, then perpendicular. Alright. So, moving on to the next one. Whoa, look at that diagram, super fun. So we're given that EHF and HFG are equal, so EHF, so that's this little tick mark here, and HFG, so that tick mark, so they've given us those. And that F and G and H, FG, GH, that's where this mark comes in. So, first thing we're going to do is write our given, which I've given 2 lines for, thanks, because we're going to write angle EHF is perpendicular to angle HFG, and then we're also going to write that FG and GH are perpendicular. Alright, so that is our multiple lined given. Then they're telling us that alternate interior angles is telling us something. So looking back at our diagram, I see, what did they give us? I see a transversal and 2 lines that are alternating on the inside of those 2 lines. So because those are alternate interior, and the fact that they are the same measure, we can then say that EH and FG are parallel. Oops. Let's say parallel. Alright, so that's those. And then finally we're going to be able to say that EH is perpendicular to GH. Let's see, EH is perpendicular to GH. Oh, that's that idea that if we have 2 parallel lines, which we just identified, and the fact that there's this one line that one of them is perpendicular to, then this one is going to have to be perpendicular as well. So, they actually said it right here as perpendicular transversal theorem. Perfect. So, that means that our final statement is this. Line EH is perpendicular to GH. Excellent. Alright, and that is the end of our notes, yep. And I would take the time to fill in your reasons packet as well. So these ones will be put in our reasons packet. I'll probably do that in the video for the assignment, but definitely want to put those in to that resource that you have.